Imagine you're falling toward the most massive object in the universe. Your watch ticks normally on your wrist. But to anyone watching from a safe distance, your movements slow, then slower, then freeze entirely. You don't stop moving. You don't die. Time itself stops flowing. This isn't science fiction. This is the documented reality at the edge of a black hole. In 1916, Carl Schwarzschild calculated something that terrified even Einstein himself, a mathematical point where the equations of spacetime don't just break down. They predict that time, the one thing we consider constant throughout the universe, can grind to a complete halt. For a century, physicists dismissed this as a mathematical curiosity, an impossibility that existed only on paper. Then we photographed it. In April 2019, the Event Horizon Telescope captured an image that shows light itself trapped in an eternal orbit, circling a point where time has ceased to exist in any meaningful way. We are witnessing the death of time at the edge of M87's supermassive black hole. What if the flow of time, the thing that defines past, present, and future, is not fundamental? What if time is something that can be created, destroyed, or frozen like matter or energy? Today, we journey through evidence that challenges everything we thought we knew about time itself. Prepare yourselves. We begin. December 1915. Europe tears itself apart in the trenches of World War I. Albert Einstein has just published his masterwork, General Relativity, equations that describe how mass warps the fabric of spacetime itself. Within weeks, a German physicist named Carl Schwarzschild, serving on the Russian front, does something extraordinary. While calculating artillery trajectories by day, he solves Einstein's field equations exactly by night. The first person to find a complete solution to the most complex equations in physics. What he discovers will haunt physics for the next century. Schwarzschild's solution describes what happens around a perfectly spherical mass. The mathematics are elegant, beautiful. But as he extends his calculations toward the center of this mass, something disturbing emerges. There's a radius, now called the Schwarzschild radius, where something breaks. At this boundary, the equations predict that time dilation becomes infinite. Not extremely slow. Infinite. To an outside observer, time at this radius literally stops flowing. Schwarzschild presents this finding to Einstein in a letter from the front lines. Einstein publishes the work but remains deeply uncomfortable. He will spend the rest of his life arguing that such objects cannot actually exist in nature. They violate, he insists, the fundamental reasonableness of the universe. Schwarzschild never learns whether his solution describes reality. He dies of a disease contracted in the trenches in May 1916, just 5 months after his discovery. He is 42 years old. His equations remain, and they contain a prophecy. Here's what Schwarzschild's mathematics predict. If you compress enough mass into a small enough space, if you cross that fatal radius, something unprecedented happens. The escape velocity at that boundary exceeds the speed of light. Not approaches it, exceeds it. Since nothing can travel faster than light, nothing that crosses this boundary can ever return. Not matter, not energy, not even information. Space and time switch roles. Outside this radius, you can move freely through space but are dragged inevitably forward through time. Inside, you can move freely through time in any direction, but are dragged inevitably inward through space, toward the central singularity. The singularity itself is even stranger. It's not a point in space. It's a moment in time. An inevitable future that exists in your past light cone the instant you cross the event horizon. For decades, physicists treat this as mathematical fiction. The conditions required, compressing the sun's mass into a sphere 3 kilometers across, seem impossible. Nature, they argue, has mechanisms that prevent such extremes. Then stars started dying. 1967 Jocelyn Bell, a graduate student at Cambridge, detects a radio signal pulsing with impossible regularity. One pulse every 1.33 seconds. Perfect. Mechanical. So precise that her team briefly considers whether it might be artificial. It's not aliens. It's something stranger. It's a neutron star, the collapsed core of a dead star, squeezed so tightly that protons and electrons merge into neutrons. A sphere 20 kilometers across containing more mass than our Sun. A teaspoon of its matter would weigh more than Mount Everest. The discovery proves that nature can compress matter to extraordinary densities. But neutron stars have a limit. Above approximately 3 solar masses, nothing can prevent further collapse. No force in physics can stop it. Gravity overwhelms every opposing pressure. The star collapses past its Schwarzschild radius. It becomes the thing Einstein insisted couldn't exist. John Wheeler, the physicist who coined the term black hole in 1967, describes the moment of formation with characteristic eloquence. A star that has exhausted its nuclear fuel undergoes gravitational collapse and cuts itself off from the rest of the universe. But here's where it gets strange. From our perspective, watching from a distance, the collapse never actually completes. The star's surface approaches the Schwarzschild radius, but as it does, time dilation becomes more extreme. The collapse appears to slow, then slow further. Asymptotically, eternally, the star appears frozen at the moment of becoming a black hole. The light from its surface gets redshifted toward infinite wavelengths. The star effectively fades from view, its light stretched into invisibility. It doesn't cross the horizon from our perspective. It gets frozen there forever. But from the perspective of matter on the star's surface, the collapse continues normally. It crosses the event horizon in finite time and reaches the singularity moments later. Two perspectives. Two completely different timelines. Both equally valid according to general relativity. But the evidence forces us to confront an uncomfortable possibility. Time is not universal. It's not the same everywhere. And at the boundaries of these objects, it may not exist at all in any way we understand. If black holes exist, they should create observable signatures. Distinctive fingerprints written in the behavior of light and matter around them. The first signature is gravitational lensing. In 1979, astronomers discover quasar Q0957 plus 561. Or rather, they discover it twice. Two images of the same distant quasar appear in the sky, separated by 6 arcseconds. A massive foreground object is bending spacetime so severely that light from the quasar takes 2 different paths around it, creating duplicate images. This is Einstein's prediction made visible. Mass warps spacetime. Light follows that curvature. But the most dramatic lensing occurs around black holes. The massive black hole at the center of galaxy M87 contains 6.5 billion times the mass of our Sun. At its event horizon, spacetime curves so sharply that light can orbit the black hole in a perfect circle, the photon sphere. From certain angles, you could theoretically see the back of your own head, light from behind you having circled the black hole to reach your eyes. The Event Horizon Telescope image from 2019 captures this effect. The bright ring we see isn't the event horizon itself, we can never see that. It's light from the accretion disk, bent around the black hole by extreme spacetime curvature. Some of that light has orbited the hole multiple times before reaching us. We're seeing light trapped in a temporal loop, circling a point where time has stopped. The second signature appears in X-ray observations. When matter falls toward a black hole, it doesn't fall straight in. Conservation of angular momentum causes it to spiral, forming an accretion disk. Friction in this disk heats matter to millions of degrees, hot enough to emit X-rays. The Chandra X-ray Observatory has catalogued thousands of these X-ray sources. What makes them distinctive isn't just their brightness, it's their variability. X-rays from black hole accretion disks flicker and pulse with characteristic patterns. Gas orbiting close to the event horizon experiences extreme relativistic effects. As it whips around at nearly light speed, the X-rays it emits get Doppler shifted and gravitationally lensed. This creates a unique spectral signature. But here's what's remarkable. We can use these flickering patterns to measure how close gas gets to the event horizon before vanishing. For some black holes, We observe matter spiraling inward until it reaches approximately 3 Schwarzschild radii, the innermost stable circular orbit. Then it vanishes from observation. Not because it stops emitting light. Because the light gets redshifted into invisibility as time dilation approaches infinity. September 1964. 2 Geiger counters launched on a suborbital rocket detect an intense X-ray source in the constellation Cygnus. Cygnus X, 1 becomes the first widely accepted black hole candidate. Here's why. Optical observations reveal a blue supergiant star, HDE 226868, with peculiar behavior. The star wobbles. Something massive and invisible is pulling on it, causing it to orbit an unseen companion every 5.6 days. By measuring the wobble, astronomers calculate the invisible companion's mass, at least 15 times the mass of the Sun. Far too massive to be a neutron star, which top out around 3 solar masses. And it's dark. Completely dark in optical wavelengths. The only light comes from the accretion disk, visible in X-rays as matter gets torn from the supergiant and spirals toward the invisible companion. The X-ray spectrum shows temperatures exceeding 10 million Kelvin. Nothing in physics can compress 15 solar masses into a dark, compact object except collapse beyond the Schwarzschild radius. Stephen Hawking famously bet Kip Thorne in 1974 that Cygnus X-1 wasn't a black hole. Hawking conceded the bet in 1990. The evidence had become overwhelming. But the most compelling evidence comes from the galactic center. Since 1992, Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute have tracked individual stars orbiting the center of our galaxy. Using adaptive optics to compensate for atmospheric distortion, they've mapped the precise trajectories of dozens of stars in the central light year. One star, S2, also called S02, has a particularly telling orbit. S2 is a massive blue star, and it orbits something invisible at the galactic center once every 16 years. Its orbit is highly elliptical. At its closest approach in 2018, S2 passed within 120 astronomical units of the galactic center, just 120 times the Earth-Sun distance. At that point, S2 was traveling at 7,650 kilometers per second, nearly 3% of light speed. From S2's orbital parameters, we can calculate the mass of what it orbits. 4.15 million solar masses, contained within a region smaller than Mercury's orbit. The density is staggering. No stable configuration of matter can be packed that tightly without collapsing beyond its Schwarzschild radius. We're watching stars orbit what can only be described as a frozen moment in spacetime, a region where time dilation has become so extreme that, from our perspective, time has effectively stopped. The object is called Sagittarius A*, pronounced Sagittarius A*. And in May 2022, the Event Horizon Telescope captured its image. But this represents just one piece of a much larger puzzle hidden in the structure of spacetime itself. 1974 Stephen Hawking discovers something that seems impossible. Black holes, he calculates, are not entirely black. Quantum effects near the event horizon cause them to emit radiation, now called Hawking radiation. This radiation carries energy away from the black hole, causing it to slowly evaporate over immense timescales. The implication is profound. Black holes have a temperature. They emit heat. They're thermodynamic objects that can eventually die. But there's a problem. A catastrophic problem that has haunted theoretical physics for 50 years. Hawking radiation, according to the original calculation, is perfectly thermal. It's random. It contains no information about what fell into the black hole. This violates a fundamental principle of quantum mechanics. Information cannot be destroyed. The quantum state of a system must always be preserved, even if transformed beyond recognition. When a star collapses into a black hole, it carries information, the quantum states of every particle it contains. When matter falls in later, it adds more information. But if the black hole evaporates into random thermal radiation, where does that information go? It appears to be destroyed, erased from the universe. This is called the black hole information paradox. and it suggests something is deeply wrong with our understanding of either quantum mechanics or general relativity, or more likely, both. Point 20124 physicists, Ahmed Almhiri, Donald Merolf, Joseph Polchinski, and James Sully, discover something even more disturbing. They prove mathematically that you cannot resolve the information paradox without violating one of three fundamental principles. 1. Einstein's equivalence principle: you shouldn't experience anything unusual crossing the event horizon. 2. Unitarity: information must be preserved. 3. The existence of an interior region beyond the event horizon. You can keep any two, but all three cannot be simultaneously true. If you insist on preserving information while maintaining an interior region, then something dramatic must happen at the event horizon. The event horizon might not be the smooth, empty boundary we imagine. It might be a firewall, a region of intense energy that incinerates anything trying to cross it. This means the smooth passage across the event horizon predicted by general relativity might be an illusion. The very concept of falling through might not apply. Or perhaps there is no interior. Perhaps black holes are not holes at all, but dense configurations of quantum information smeared across the event horizon, a holographic encoding of everything that fell in. From the outside, we would never know. Time dilation prevents us from ever witnessing what actually happens at the boundary. September 14, 2015. 9:50 and 45 seconds Universal Time Coordinated. After decades of construction and calibration, the LIGO detectors pick up a signal. The signal lasts 0.2 seconds. In that fraction of a second, it sweeps upward in frequency from 35 Hz to 250 Hz, then cuts off abruptly. The signal matches, with stunning precision, the predicted waveform from two black holes spiraling together and merging. The black holes had masses of 36 and 29 solar masses. They orbited each other at increasing speed, their orbital velocity reaching 60% of light speed in the final moments before merger. The collision released more energy than all the stars in the observable universe combined, emitted in a fraction of a second. 3 solar masses converted entirely into gravitational waves. The detection confirms multiple predictions. Black holes exist and can form naturally from stellar collapse. Black holes can orbit each other in binary systems. Black holes can merge, creating a larger black hole. Gravitational waves propagate at exactly the speed of light. Einstein's equations accurately describe extreme spacetime dynamics. But here's what's most remarkable. The gravitational wave signal cuts off at the moment of merger. Not because the black holes stop emitting waves, but because the newly formed event horizon swallows the remaining oscillations. We're detecting the gravitational sound of spacetime itself being crushed out of existence. Since 2015, LIGO and its counterpart Virgo have detected over 90 black hole mergers. We're witnessing the deaths of time itself on a regular basis. Recent computer simulations reveal something strange about the photon sphere, the radius where light can orbit a black hole. If you were to hover just outside the photon sphere and shine a flashlight in any direction, the light would curve around the black hole and hit you in the back of the head. You would be illuminated by your own flashlight beam, having circled the black hole. But here's the paradox. From your perspective, the light takes normal time to complete the orbit, perhaps a fraction of a second for a stellar mass black hole. But to someone watching from a distance, the light's journey appears to take longer due to time dilation. Much longer. For an observer far away, they would see the light taking an infinite amount of coordinate time to complete each orbit. The light would appear to slow down, redshift, and eventually fade from view. Two different observers see two different realities. Both are correct within their reference frames. This isn't just philosophical speculation. This is a direct prediction of general relativity, confirmed by the light patterns we observe around M87's black hole. The evidence extends beyond observations into the realm of theoretical physics, where the implications become truly reality-shattering. What is an event horizon, really? It's not a physical surface. There's no material barrier at the Schwarzschild radius. If you fell across it, you'd feel nothing unusual. The spacetime there is, in a mathematical sense, unremarkable. But it represents something profound, a causal boundary. Events inside the horizon cannot influence events outside. Information cannot propagate outward across this boundary because doing so would require exceeding the speed of light, and the inward curvature of spacetime makes this impossible. The event horizon is, fundamentally, a point of no return in spacetime geometry. But here's what contemporary physicists are discovering. The event horizon may not be as simple as Einstein thought. When quantum mechanics meets general relativity at the event horizon, strange things happen. Hawking's original calculation showed that quantum fluctuations near the horizon create particle-antiparticle pairs. Normally, these pairs annihilate immediately. But near the horizon, one particle can fall in while the other escapes. This escaping particle becomes Hawking radiation. From the outside, it appears the black hole is evaporating. But recent work by theorists including Leonard Susskind, Juan Meldacena, and others suggests something more radical. The event horizon might be a hologram. The holographic principle proposes that all the information about the three-dimensional interior of a black hole is encoded on its two-dimensional event horizon surface. The interior might not exist independently. It might be an emergent property of the quantum information stored on the horizon. This would mean that the experience of falling through the event horizon and continuing to the singularity is somehow encoded in quantum states on the surface. The interior spacetime we calculate in general relativity might be a holographic projection of boundary information. What exists at the center? General relativity predicts a singularity, a point of infinite density where spacetime curvature becomes infinite and the equations break down completely. All matter that falls into a black hole gets compressed to this point, creating infinite tidal forces that tear apart anything approaching it. But infinity appearing in physics usually means our theories have reached their limits. Most physicists believe the singularity isn't physically real. It's a sign that general relativity fails at extremely small scales, where quantum effects become dominant. Several theories attempt to resolve this. Loop quantum gravity suggests that spacetime itself is quantized at the Planck scale, the smallest possible unit of space, about 10 to the power of -35 meters. Instead of collapsing to a point, matter might compress to Planck density and then bounce, potentially creating a white hole that erupts into another universe. String theory proposes that at sufficiently small scales, the point-like singularity gets smeared out into extended objects. The mathematics show that string theory might make the interior of black holes fundamentally ambiguous. There might not be a single classical interior geometry. Causal set theory suggests that spacetime emerges from a discrete structure of causal relations. In this framework, the singularity might simply be a point where this causal structure terminates, not unlike how a function can have a defined endpoint without causing mathematical paradoxes. No one knows which approach, if any, is correct. Here's the most profound aspect: time itself behaves differently at the event horizon. In general relativity, time is measured by the interval along a world line, the path an object takes through spacetime. Different world lines accumulate different amounts of proper time. This is time dilation, and it's been measured countless times in experiments. But at the event horizon, something extreme happens to the coordinate time, the time measured by distant observers. A clock falling toward the horizon appears to run slower and slower to distant observers. As it approaches the horizon, each tick takes longer than the last from the external perspective. The clock asymptotically approaches infinite redshift. From the distant observer's coordinate time, the clock never actually crosses. It's frozen at the boundary forever. But from the clock's perspective, it's proper time. It crosses the horizon in finite time and reaches the singularity moments later. This isn't a paradox. It's a feature of curved spacetime. The horizon represents an infinite coordinate time future for external observers, but a finite proper time future for infalling objects. Kip Thorne describes it elegantly. The horizon is the place in time where space becomes so strongly curved that it forces matter and light to flow only inward. Time doesn't stop at the horizon, but the definition of time becomes frame-dependent in a way that has no analog in our everyday experience. This forces us to reconsider fundamental assumptions about the nature of time itself. The Event Horizon Telescope observations of M87 and Sagittarius A** represent just the beginning. These images show the shadow of the black hole, the dark region from which no light can escape, surrounded by the bright emission from the accretion disk. The size and shape of this shadow directly test general relativity's predictions. So far, the observations match Einstein's equations with stunning accuracy. The shadow size corresponds precisely to what we calculate for a black hole of the measured mass. But future observations will probe deeper questions. The next generation Event Horizon Telescope, with additional radio telescopes and space-based components, will achieve higher resolution. We'll see fine structure in the accretion flow. We'll observe how matter behaves in the final moments before crossing the horizon. The gravitational wave detectors LIGO, Virgo, and the upcoming LISA space interferometer will detect thousands more black hole mergers, probing how black holes form, evolve, and interact. Hawking radiation from astrophysical black holes is impossibly faint. A solar mass black hole has a temperature of 60 nanokelvins, 60 billionths of a degree above absolute zero. It would take 10 to the power of 67 years to evaporate, far longer than the current age of the universe. We'll never detect Hawking radiation from real black holes. But in 2016, Jeff Steinhauer at the Technion created an acoustic analog of a black hole in a laboratory. Using flowing Bose-Einstein condensate, he created a boundary where the flow velocity exceeds the speed of sound. Sound waves cannot escape past this boundary, just as light cannot escape a black hole's event horizon. Steinhauer detected the sonic equivalent of Hawking radiation, phonon pairs created at the acoustic horizon. While not identical to gravitational black holes, these acoustic black holes provide experimental confirmation of Hawking's quantum mechanical predictions. Recent breakthroughs suggest we might create electromagnetic black hole analogs using metamaterials, allowing us to study horizon physics in the laboratory. The black hole information paradox remains unresolved, but progress is being made. In 2019, Jeff Pennington, Stephen Schenker, Douglas Stanford, and others calculated something remarkable. They showed that information does eventually escape from evaporating black holes, but in an incredibly scrambled form. The information comes out encoded in subtle correlations in the Hawking radiation, correlations that build up over time. This suggests that black holes are not information destroyers but information scramblers. The information about what fell in eventually comes back out, but in a form so chaotic that it's effectively irretrievable. The calculation uses techniques from string theory and quantum information theory. It suggests that the interior of a black hole is fundamentally related to its exterior through quantum entanglement in ways we're only beginning to understand. An intriguing possibility has emerged. Some of the universe's dark matter might be black holes. In the first fractions of a second after the Big Bang, density fluctuations might have been large enough to create black holes directly. Primordial black holes that never formed from stellar collapse. These primordial black holes could have masses ranging from tiny, smaller than an asteroid, to millions of solar masses. If enough formed in the right mass range, they could account for some or all of the dark matter we observe. Recent observations from gravitational wave detectors showing black hole mergers with unexpected masses have renewed interest in this idea. Some of the merging black holes have masses that are difficult to explain through standard stellar evolution. They might be primordial. A radical perspective is emerging in theoretical physics. Black holes might be the universe's most efficient information processors. The Bekenstein-Hawking entropy formula tells us that a black hole's entropy, its information content, is proportional to the area of its event horizon, not its volume. This is strange. Normal objects have entropy proportional to their volume. This suggests something fundamental. The maximum information content of any region of space is determined by the area of its boundary, not its volume. This is the holographic principle, and it implies that our three-dimensional universe might be a holographic projection of information stored on a two-dimensional boundary. If true, this would mean that black holes aren't exotic objects but rather windows into the fundamental structure of spacetime itself. They reveal that space might be an emergent phenomenon, not a fundamental one. Understanding black holes is inseparable from understanding quantum gravity, the theory that will unite general relativity and quantum mechanics. Black holes are where these theories collide. General relativity predicts smooth event horizons and interior spacetime. Quantum mechanics predicts that information cannot be destroyed. Both cannot be completely correct as formulated. The resolution will tell us what spacetime is made of at its most fundamental level. Loop quantum gravity suggests spacetime is woven from quantum threads. String theory suggests it emerges from the vibrations of fundamental strings. Other approaches suggest spacetime itself might be emergent from quantum entanglement. Black holes are the laboratories where these ideas will be tested, not through direct observation but through their theoretical implications and the consistency of the mathematics. The most profound implications emerge when we consider what black holes tell us about the nature of reality itself. Black holes reveal something extraordinary about time's arrow, the distinction between past and future. The second law of thermodynamics states that entropy always increases. This is why eggs break but never spontaneously reassemble, why heat flows from hot to cold, why we remember the past but not the future. The increase of entropy defines time's direction. But black holes have entropy. The Beakenstein-Hawking formula gives this entropy a precise value, 1/4 of the event horizon's area in Planck units. When matter falls into a black hole, the black hole's entropy increases. Information gets scrambled beyond retrieval. From the universe's perspective, entropy has increased dramatically. Black holes are entropy generators. They might be the universe's primary drivers of the second law of thermodynamics. This suggests something profound. The arrow of time might not be a fundamental feature of physics. It might emerge from the existence of these cosmic information scramblers, these regions where time becomes directional by becoming one way. If the interior of a black hole is cut off from our universe by an event horizon, what prevents it from being its own universe? Some cosmological models suggest that what we experience as the Big Bang might be the interior of a black hole as seen from the inside. Our expanding universe might be the interior geometry of a black hole that exists in a larger parent universe. This leads to a staggering possibility. Every black hole that forms in our universe might spawn a new universe on the other side of its event horizon. Universes within universes, nested like Russian dolls, each invisible to the others. Lee Smolin proposed this as cosmological natural selection. Universes that form many black holes produce many offspring universes. Over cosmic generations, the fundamental constants of physics might evolve toward values that maximize black hole formation. This would explain why our universe's constants seem fine-tuned for complexity. We exist in a universe descended from a long line of black hole-producing ancestors. It's speculative, untestable with current technology, but it's a natural extension of general relativity's mathematics. If black holes contain singularities, points where spacetime curvature becomes infinite, they share this feature with the Big Bang. The Big Bang, according to general relativity, began with a singularity. All of space was compressed to a point of infinite density 13.8 billion years ago. From this singularity, space and time emerged. But if singularities don't physically exist, if they're mathematical artifacts indicating where our theories break down, then what does this tell us about the Big Bang? Perhaps the Big Bang wasn't a beginning, but a transition. Perhaps our universe emerged from the collapse of a previous universe, bouncing at the Planck scale when quantum effects became dominant. Perhaps time existed before the Big Bang in a form we don't yet understand. Black holes and the Big Bang might be the same phenomenon viewed from different sides. Gravitational singularities where our understanding of spacetime reaches its limits. The most radical implication of black hole physics is this. Time might not be fundamental. In quantum mechanics, time is treated differently from space. Space is an operator that can have uncertainty and superposition. Time is a parameter, a fixed background against which quantum events unfold. But general relativity treats time and space on equal footing. They're both components of spacetime, equally dynamic and relative. Reconciling these views might require abandoning the notion that time is fundamental. Perhaps time emerges from something more basic, from quantum entanglement, from information flow, from causal structure. Several approaches suggest this. Carlo Rovelli's relational quantum mechanics proposes that time emerges from correlations between quantum systems. There is no universal time, only relationships between events. The Wheeler-DeWitt equation, which attempts to quantize gravity, contains no time parameter at all. The universe, in this view, doesn't evolve through time but exists as a timeless quantum superposition of all possible configurations. Black holes, where time behaves so strangely, might be showing us that time is not fundamental but emergent, a useful approximation that breaks down at extremes. If you fell into a black hole carrying information, say, an encyclopedia, what happens to that information? According to classical general relativity, it crosses the event horizon and eventually reaches the singularity. The information is destroyed. According to quantum mechanics, information cannot be destroyed. It must persist somewhere, somehow. According to the holographic principle, the information gets encoded on the event horizon itself, stored in the quantum states of the horizon's degrees of freedom. According to recent calculations, the information slowly leaks back out in Hawking radiation, scrambled beyond recognition but preserved in subtle correlations. Each interpretation has implications. If information is destroyed, quantum mechanics is incomplete. We need new physics that allows information destruction under certain extreme conditions. If information is preserved on the horizon, the interior might be an illusion, a holographic projection that doesn't independently exist. If information leaks out in Hawking radiation, then black holes are temporary storage devices, not permanent information prisons. The resolution will tell us something fundamental about the relationship between information and reality. Here's a final, vertiginous possibility. From outside a black hole, infalling matter appears frozen at the event horizon, time dilated to infinity. From inside, time flows normally and space expands toward the singularity. From outside our universe, the Big Bang happened 13.8 billion years ago. From inside, space has been expanding ever since. The mathematical similarity is striking. Some cosmological models are mathematically equivalent to the interior of a black hole. This suggests a possibility: we might be living inside a black hole. Our expanding universe might be the interior geometry of a black hole that exists in a larger parent spacetime. From outside, we would appear as a black hole, a region of space that collapsed and cut itself off from the exterior. From inside, we experience expanding space and flowing time. The cosmic microwave background, the afterglow of the Big Bang, might be the redshifted light from the moment our universe's parent region crossed its own event horizon. This is speculation, but it's mathematically consistent speculation rooted in general relativity's equations. We stand at the boundary of knowledge, peering into the abyss where time itself transforms into something stranger than we can imagine. We began with a simple question: what happens to time at the edge of a black hole? The journey has taken us from Schwarzschild's battlefield calculations through Hawking's quantum revelations to the Event Horizon Telescope's stunning images. We've seen that black holes are not merely massive objects but fundamental features of spacetime geometry, places where time becomes directional, malleable, and possibly emergent. The evidence is overwhelming. Black holes exist. They form from stellar collapse, merge in spectacular collisions, and lurk at the centers of galaxies. We've photographed their shadows, detected their gravitational waves, and watched stars dance around them for decades. But what we've truly discovered is far stranger than massive objects in space. We've discovered that time, the one thing we assumed was universal and constant, is neither. Time flows differently depending on where you stand and how fast you move. At the event horizon of a black hole, time from an external perspective effectively stops. From an internal perspective, it flows normally until spacetime itself terminates at the singularity. Two truths, both correct, both irreconcilable from a single viewpoint. This tells us something profound. The universe doesn't have a single timeline. There is no universal now that extends throughout space. Reality is not a series of successive moments but a four-dimensional structure where time and space interweave in ways that depend on mass, motion, and geometry. Black holes are the extreme laboratories where we confront this truth most directly. The current scientific consensus holds that black holes form naturally from stellar collapse and gravitational dynamics. Their properties are accurately described by Einstein's general relativity. Quantum effects near the horizon create radiation that causes eventual evaporation. Information is ultimately preserved, though in highly scrambled form. The singularity indicates where our current theories break down. A complete theory of quantum gravity will resolve remaining paradoxes. Yet mysteries remain. We don't know what happens at the singularity. We don't fully understand how information escapes in Hawking radiation. We can't observe the event horizon's interior. We haven't unified quantum mechanics with gravity. These are not failures of science. They're invitations. The universe is revealing itself layer by layer. Each answer spawns new questions. Black holes show us that time is not what we thought it was. And if time isn't fundamental, what else about reality is emergent rather than basic? Perhaps space itself. Perhaps causality. Perhaps consciousness. We've learned that we live in a universe where time can die, where information might be holographic, where the interior and exterior of regions can be causally disconnected yet mathematically related. A universe stranger and more wondrous than we imagined. And we've only just begun to understand. The next generation of telescopes will see deeper. The next generation of gravitational wave detectors will hear more clearly. The next generation of physicists will solve equations we haven't yet written. The black holes remain, patient and eternal, waiting at the edge of eternity. Waiting for us to understand what they've been showing us all along. That time is not a river flowing from past to future. Time is a landscape. A geometry, a relationship between events, and at the boundaries of black holes, that landscape terminates, or transforms into something we have yet to name. The universe is vast. The mysteries are endless. The journey continues.